Hello, viewers. In today's session, we are going to discuss an important conceptual problem from differentiability of functions. And in this class, we are going to discuss this problem in which we are given a function f of x that is equal to greatest integer of x minus 2, and we have to discuss or examine the differentiability of this greatest integer function at this point, that is x is equal to 1, right? So here we have a function which is a greatest integer function, and we have greatest integer of x minus 2, and we have to test whether this function is differentiable or non-differentiable at this point x is equal to 1. So with the help of the concept of right hand derivative and left hand derivative, we'll check the differentiability of this function. So now we know that if we are given a function, say y is equal to f of x, and if we have a point, say x is equal to a in the domain of this function f of x, and if this function is differentiable at this point, that is x is equal to a, then the right hand derivative and the left hand derivative, both these derivatives must exist and they should be finite, and moreover these two derivatives should be equal. So a function is said to be differentiable at some point x is equal to a in the domain of f of x if the right hand derivative and the left hand derivative are both equal, and they should exist and they should be finite. So let us find out the right hand derivative and left hand derivative for this function at this point, that is x is equal to 1, right? So let us start with the right hand derivative, and the right hand derivative is defined by this limit, that is limit h tends to 0, and here we have f of a plus h minus f of a divided by h, right? So a is the required point where the differentiability is to be examined, right? And the notation for the right hand derivative may be taken as f prime, and here we have a, and here we can take a positive sign. So here in this case the value of a is 1. So we can now write f prime, and here we have the positive sign, here we have 1, and the right hand derivative is given by limit h tends to 0 f of 1 plus h minus f of 1 divided by h. And remember, this h is infinitesimally very small, and it lies between 0 and 1, right? So h is a positive quantity lying between 0 and 1. Okay, so now let us first find out the value of f of 1. So f of 1 can be given by taking x is equal to 1 in this function. So we have greatest integer of 1 minus 2. So this is greatest integer of minus 1, right? And we know that the greatest integer of an integer is the integer itself, right? So now we have a limit h tends to 0, and f of 1 plus h can be given by replacing x by 1 plus h. So we have 1 plus h minus 2, and f of 1 is minus 1, right? Okay, so let us simplify it. We have limit h tends to 0, and here we have greatest integer of 1 plus h minus 2. So this is h minus 1, greatest integer of h minus 1, and here we have plus 1 divided by h. So now we need to find out the value of greatest integer of h minus 1, right? Because we have to solve this limit, and in order to get the value of this limit, we have to assign value to greatest integer of h minus 1 using this concept or this inequality, right? Okay, so now here if we subtract 1 throughout in this inequality, then we get 0 minus 1, then we have h minus 1, and here we have 1 minus 1. So this is minus 1, this is h minus 1, this is 0. So this inequality suggests that h minus 1 lies between minus 1 and 0, right? Here we have 0 and here we have minus 1. So this h minus 1, it lies somewhere between minus 1 and 0. So the greatest integer of h minus 1 should be equal to minus 1. So the value of greatest integer of h minus 1, by the definition of greatest integer function, the greatest integer of h minus 1 should be equal to minus 1. So here we can replace this quantity by minus 1. So we have limit h tends to 0, and here we have minus 1 plus 1 over h, right? Now minus 1 plus 1 is 0, so this entire limit reduces to 0, right? So the right hand derivative of this function at x is equal to 1 is equal to 0. So the right hand derivative is equal to 0. Now let us find out the left hand derivative. So the definition of left hand derivative is given by the limit, that is limit h tends to 0, and we have f of a minus h minus f of a divided by minus h, and the notation may be written like this. Here we have f prime of a, and here we put a negative sign, right? So the left hand derivative is now equal to limit h tends to 0. We have f of 1 minus h, and here we have f of 1 divided by minus h. This is limit h tends to 0. F of 1 minus h can be obtained by replacing x by 1 minus h. So we have greatest integer of 1 minus h minus 2, and f of 1 we have already calculated. This is minus 1 over minus h. So this is limit h tends to 0, and this is greatest integer of minus h minus 1, and here we have plus 1 over minus h, right? So now we have to calculate or evaluate this limit. So let us assign a value to this term, that is greatest integer of minus h minus 1. So again we'll utilize this inequality, that is h greater than 0 but less than 1. So let us multiply this inequality throughout by minus 1, right? So we have 0, and the direction of the inequality get reversed, and when we multiply throughout by a negative quantity, here we have minus h and here we have minus 1. So let us subtract minus 1 throughout so that we can get the term minus h minus 1. So here we have 0 minus 1, here we have minus 1, and here we have minus 1, right? So here minus 1, this is minus h minus 1, this is minus 2. So this inequality can be rewritten as minus 2 is less than minus h minus 1, and here we have minus 1, right? So now this inequality suggests that minus h minus 1, it lies between minus 2 and minus 1. So here we have 0, here we have minus 1, and here we have minus 2. So this quantity minus h minus 1, it lies between minus 2 and minus 1. So minus h minus 1, it lies somewhere between minus 2 and minus 1. So the greatest integer of minus h minus 1 should be equal to minus 2. So here we have minus 2. So now we can write the limit as limit h tends to 0, and this quantity is now equal to minus 2. So here we have minus 2 plus 1 over minus h, and this is limit h tends to 0. 1 minus 2 is minus 1 over minus h. So this negative and this negative get cancelled. So we have limit h tends to 0, 1 over h, right? So when h tends to 0, then 1 over h tends to infinity, or it is not defined, right? So we can see that this limit tends to infinity, that is not defined. Hence we can conclude that the left hand derivative is not finite, right? So the left hand derivative is not defined here, and from this result we can conclude that although the right hand derivative it exists and it is finite, but it is not equal to the left hand derivative, or in other words the left hand derivative is not defined. So we do not have a unique tangent to this curve at this point, that is x is equal to 1. That's why this function is now not differentiable at x is equal to 1. So we can conclude that the greatest integer of x minus 2 is not differentiable at this point x is equal to 1, because the right hand derivative is not equal to left hand derivative, right? So this is how by making use of the concept of right hand derivative and left hand derivative, we can examine the differentiability of a function at a given point.